Hey students, this is lesson 214. What we're going to do here is learn how to fit lines to data that isn't quite perfect. And we're going to use a couple methods of doing that, including technology. Important vocab here is that a line of best fit is a line that fits all of the data points as closely as possible. This example here kind of gives you an idea of what we might be going at here. These students are measuring how far a wagon goes every time the wheels rotate once. So the wheels of the cart are 2.5 feet in circumference. So how far is the wagon going to go? And as I'm thinking about this, I'm thinking the wagon should go 2.5 feet every one rotation. But these students didn't really know that, and so they just took some data. And notice their data points do not line up straight in a line. And that's because when you measure something in real life, you can't get it perfectly. But what we're going to try and do in this lesson is, even though our data isn't perfect, we're going to try to estimate, if it looks like it lines up, a line that kind of fits that data, and then we're going to use that line in the equation for that line to help make predictions. Okay? So, I'm going to do this first problem with you. In this table, there's a relationship between the heartbeats per minute and the breaths per minute. Turns out that the more breaths per minute you have, the faster your heartbeat is going to go. And this data was taken after students had walked for 20 minutes. And there's 16 people here, so there's 16 pieces of data. This is the first person, the second person, the third person, and so on. Now, if you plot that data with breaths per minute on the x-axis and heartbeats per minute on the y-axis, you get a graph that looks like this. Now, there is a pattern here. Notice that these dots go in a line. It's just that they're kind of spread out a little. And since they kind of go up in a line, we can assume that there might be a linear relationship here. And what we're going to do is draw a line so to represent those points. Now, when I draw a line, I'm just going to kind of eyeball it, and that's why this is called the eyeballing method. But I'm going to draw my line here, and what I'm going to try to do is make sure there's about the same number of points above the line as below the line. Now notice if I move my line up here, it doesn't really match it very well, but it does match the slope of those dots about the same. Same with here, it's a little bit too low. So if I put it right about in the middle there, then I think I have a pretty good line. Now, if you had a line like this, you could also split the dots, but the slope of that line doesn't match the slope of the dots. So that's not a very good line to help you make predictions. So we want to get about the same slope and split so that the number of dots is the same above and below the line. And once we have that, we're going to write the equation of the line that we drew, and then we can use that to help predict some things. So remember, on a linear equation, what we need are two things. We write it in slope-intercept form. We need the slope and the y-intercept. I can estimate my y-intercept just by looking at the graph that's down here, and it looks like it's about 15. So let's write that down. Y-intercept is the point 0.015. And now the slope, I just, one way I can get the slope is to just pick 2 points that are on the line and then use those 2 points to find the slope. Like, notice this one and this one here. They are really close to that line. They're like right on it. And so if I can find those data points and use those values, one of those looks like about 36 and the other one looks like a little over 40. So 36 and 40. If I go back to my table, I'm thinking it's these two right here. So if I subtract, these are my y values, these are my x values. If I do 116 minus 105 and divide that by 41 minus 36, 116 minus 105 is 11, 41 minus 36 is 5. 11 divided by 5 is 2.2. That is my slope, 2.2. So we can write that. My slope is 2.2. And now I can write an equation. And the equation is y, which is my heartbeats per minute, is equal to 2.2 times x plus my y-intercept, which is about 15. Now, the way I did that wasn't super accurate, and we can improve our accuracy by doing certain things, and I'll talk a little bit about that. But at this point, if I wanted to make some predictions, like maybe I wanted to know how many heartbeats per minute somebody who had 50 breaths per minute is, you could just look at the graph and estimate that it's about 136 maybe. Or you could use your equation and just plug in 2.2 times 50 plus 15 now. And 2.2 times 50 is about 110 plus 15 is about 125 according to my equation. So equation makes it a little easier to make predictions. All right. Let's see what we can do to improve this line a little. It says, one technique for improving the fit of your line is to use the means of the data. So going back and looking at the table, what would be the mean? Mean is the average of the breaths per minute, and what would be the average of the heartbeats per minute? To get those averages, I need to add up all these values and divide it by 16. Add up all these divided by 16. And I'll do that for you. So when I add up all the breaths per minute, I get 432 divided by 16 is 27. When I add up all the heartbeats per minute, so this is my x, and this is my y, heartbeats per minute, I get 1,318 divided by 16 equals 82.375. Let's just round that to 82. So about 82. All right, that's my mean x and mean y. Now, I'm going to locate that point, 27, 82. So 27 is about right. Let me put a dotted line there for you. 27 is about right here. And 82.5 is, this line right here is 75, so 80 is about here, maybe about right in there. Okay, so I want my line to go through that because I know that's the average. And if my line goes through the average, then it's going to be a little bit better predictor of the actual. So I'm going to move that up a little, and I'm going to move this down a little just so I can get about the same above and below. That changed some things a little bit. So we'll go through the green line. All right, maybe move this down just a little bit, move this up a little bit. So it goes through the green dot. All right, and then I can use that point to get my equation. So I have 2782. Again, I'll need the slope. And this time I think I'll just pick another one that I know is on that line, which is right there. And that one's the one that's at about 16. So 16 is the higher one of the two. So 1659, I'm going to use that. 1659. I'm going to subtract 82 minus 59 and 27 minus 16 to get the slope. So this time my slope is 2.1. And to find the y-intercept, I'm going to actually use one of these points to help me do that. So I know my equation now is 2.1x plus some y-intercept. And I'm going to substitute 59 for y. 2.1 times 16. And if I multiply 2.1 by 16, I get 33.6. If I subtract that from 59, I get 25.4. So that's my y-intercept, 25.4. And that should be a little bit more accurate because it goes through the mean. Now, I'm going to use that equation, 2.1x plus 25.4, to make a prediction, number 4 here. Y equals 2.1x plus 25.4. It says, use your equation to predict the heart rate for a person who has 35 breaths per minute. So all I'm going to do is take 2.1 times 35 plus 25.4. I'm going to let you do this and we'll check your answer in class. Also, make a prediction about a person that who takes 100 breaths per minute. So put 100 there also and see what you get, and decide whether or not that's reasonable. And we'll talk about that in class. All right, that's it. See you tomorrow.